and one or two abroad. So that should be a bit of fun as well. Great to be able to do all these talks online. And then after our main speaker, we'll tell you a little bit what's happening in the future. There's a big Irish and indeed British eclipse coming up in only a few weeks' time, and loads happening with Mars in the sky and other things like that. A couple of radio interviews as well, if you want to hear more of the familiar voices this evening. So that's our format for the evening. My name is David Moore. I'm the founder of Astronomy Ireland and editor of Astronomy Ireland magazine. We've had new people joining the club from all over the country this year, which has been a bit of an unusual past year, to say the least. But it was also our 30th birthday, technically August the 1st last year. So from August 1st last year to July 31st this year, we're celebrating our 30th anniversary. So this, the silver lining of this big cloud we've had has been that our membership has gone through the roof. It's almost doubled in just those 12 months with the lockdowns that have been caused as people turn back to their hobbies, not just astronomy, but other clubs around the world have reported the same thing. Apparently, our telescope shops are sold out of their telescopes, which is sort of a good thing to be able to report. So we hope you, if you're not already a member, that you will join Astronomy Ireland. We have a fantastic magazine that comes out every month, tells you all about Irish astronomy. I'll tell you some notes about what to see in the next month that come from the April issue, which those of you who are members should well have by now. So a little bit about what we do. Well, we're Ireland's monthly magazine, but we also run lots of events like any society. There are these lectures every month. If you go to our website, astronomy.ie, over on the menu at left, you'll see DVDs that you can get of past lectures going back over a decade, as well as our distinguished speaker this evening. We've had people like the BBC's rockstar astronomer, Professor Brian Cox. We've had talks by astronomer royals and lots of interesting talks on both space, as we're talking about here, the manned use of space, right the way through to cosmology, where the universe came from, and all the planets and other spacecraft missions and everything in between, everything under the sun and beyond. So do enjoy having a look at the past lectures as well. You can still watch them on DVD if you see any that take your interest. We also do evening classes twice a year. We've just come to the end of our early year batch, but our new batch are enrolling now. They start in October every Wednesday evening. Just go to astronomy.ie. Again, you'll see the evening classes listed there. You can sign up now or sign up a friend if you want. We used to run lots of telescope watches. They're on hold at the moment, given the current restrictions, but we're dying to get back and show people the moon, planets and eclipses through telescopes live. So follow us on our social media and you'll see announcements for those hopefully in the coming months as things open up. The big event we run every year is Ireland's biggest annual star party. It's called Starbecue, a barbecue under the stars. It had to be postponed last year, but we have it provisionally set for the 4th of September, and things looking okay that it will probably go ahead this year. But let's wait till June or July before we make our final minds up on that one. But that is the biggest annual get-together of astronomers all over Ireland. We've had up to 600 people. We're hoping for something special for our 30th anniversary. We also do talks in schools. Done a few of those online, but not that many with the schools being out this year. But we hope to get back to doing those again. So you can book those with us. Go to our website. You'll see details there. Of course, one thing we do, because we believe we are the world's most popular astronomy club, is we have a huge media presence. So since the last lecture, 4 weeks ago, is it? We've had national radio interviews on News Talk. We've even done interviews with the BBC. And there's 2 more interviews coming up, one on Friday and one on Friday week that we already have booked in. I'll tell you about those after our main speaker. Another thing you may have seen was that we had very good coverage in the Irish Independent. I think it was March 23rd, when they did a full feature on how hobbies like astronomy are booming. And there was some of our new members were interviewed especially for that. We gave a very good account of themselves and why, this is a fascinating hobby. We're maybe a bit biased thinking it's the best hobby in the universe, but I think we can justify that if anybody wants to argue with me later on. But going back to our last meeting and covering some of the events that came up, our last lecture was by Laura Murphy from Trinity College Dublin, who was talking about the first stars in the universe. So after the Big Bang, eventually things cooled down enough for the first stars to form, and they were monsters, as she explained in her talk. If you missed that, You can get it on DVD. I think we might still have it online as well. So just follow the link on the DVD page there. They'll tell you if you want to watch it online or by DVD. That was thanks to Laura Murphy from TCD. I'll tell you about our next talk after our main speaker this evening. The other thing that happened, of course, we'd like to tell you about the BBC Sky at Night program. Watched it myself last night on BBC 4. If you missed it, it's all about Mars, the cover story on the April magazine, which is that meteorite fall, the first in 30 years on the British Isles. So watch out for that being repeated on BBC 4 Thursday night, just before midnight, I saw on the listings. So that's this BBC Sky at Night. Linking in with what's been going on in the sky, which we like to cover in the magazine a lot, we've had two sort of unexpected events. There was a comet we mentioned in the magazine called 2020 R4, Comet Atlas, probably an easy way to remember it. And it is beginning to brighten up. I've seen it myself, taken a few pictures of it. You have to get up early to see it at the moment, but it will come into evening sky. And over the next couple of weeks, it's going to be closest and brightest. And you might be able to see it in binoculars. There's a star chart in the April magazine, so don't forget about Comet Atlas. Another thing that happened unexpectedly was a new star exploded in the constellation of Cassiopeia. I'll tell you a bit more about that after the main talk, but it's just about visible in binoculars. Not the brightest thing we've ever had, but for the experts, those of you who are getting into binocular astronomy now, this is the brightest one I think we've seen since 2014. So that's quite a rare event. And it's visible all night long in the constellation of Cassiopeia near the W. I'll explain a little bit more about that after the talk. So getting back to the space theme before I introduce our speaker, one thing we love doing is predicting the International Space Station. And it just ended a set of evening passes there last week. It'll be back though in the middle of May. You'll be able to see it for about 3 weeks, 2 or 3 weeks anyway. And I'm sure this will be a topic of our main talk this evening. So, do plan to watch that and follow our social media, Facebook and Twitter, especially, where every day we post interesting satellites to watch. So that's either the International Space Station. By the way, it will be in morning skies in a couple of weeks' time, if you like getting up at 5, 6 o'clock in the morning. But if you don't, just wait till the middle of May and you'll get it in the evening. The other thing we predict are these Starlink satellites. They're very interesting after they've just been launched. We're all worried they may ruin the night sky. But after launch, you can see up to 60 satellites, all in a short train chasing each other across the sky. Then as they move to higher orbits and they hopefully engage those dark shields they're talking about, they dim away, and they've been difficult to see recently. But we have one prediction on our social media tonight. I think it's for just after 9 o'clock. Check the social media, just after 9:30, and watch out for that. Let us know if you do see it. So that's another excuse to follow us on social media, which of course is completely free of charge. And then the other space news that's happening is on March 31st, the European Space Agency opened up applications for astronauts from Ireland, because we're a member of the European Space Agency. So do check that out on their website, esa.int. And we send out a weekly email to all paid up members. And the links to that were in last week's email, and we'll put them into tomorrow's email. They usually go out on Tuesday nights. Just remind you of things to see and tell you of any new things to see. So membership has its benefits, as I say. And all that space news brings us nicely to the topic of this evening. We're delighted to have Dr. Martin Braddock, who is a professional scientist and a project manager working in the field of drug discovery and development. He has 30 years experience of working in academic institutions and for large corporate organizations. He holds a primary degree in biochemistry and a PhD in radiation biology. He's been a fellow at the University of Oxford and worked in academia, but he's also the author of over 180 peer-reviewed publications, a member of several scientific advisory boards. He's a listed inventor on 8 patents, and he's given lectures all over the world. He has a serious interest in astronomy as well, and in 2015 was elected a Fellow of the Royal Astronomical Society. He's passionate about all aspects of astronomy, cosmology, astrobiology, and holds university qualifications in cosmology, astronomy, and planetary science, astrobiology from the University of Central Lancashire, and the Open University. And he's working towards an MSc in space science and technology. Martin, on the amateur front, is an active committee member of the Mansfield and Sutton Astronomical Society and Newton's Astronomical Society at Woolsthorpe. But he has a lifelong interest in teaching people science. He's very enthusiastic about that. A great fan of online learning. That's why he joins us here this evening. He sees it as his duty to help inspire the next generation of potential young scientists, and he'll get no argument from us on that front. We love giving talks in schools as well. So he's going to explain what a lot of goes on in space. We often say that there's new drugs and medicines being produced, but here's a man who knows all the details of it. So without further ado, please give a warm welcome to Dr. Martin Braddock. Over to you, Martin.
Thank you very much, David. Let me make sure that this works okay. And can everybody see the first slide?
Yes, I can.
Perfect. So thank you very much, David, and thank you very much for the kind introduction. So in about the next 45 minutes or so, what I'd like to do is illustrate a little bit about drug discovery and drug development, and how the space environment could help us. And I've called this a little bit of tongue-in-cheek, the best of all worlds, because for me, this pretty much is the best of all worlds. It marries up drug discovery and drug development, which is what I do professionally, with what I would like to do professionally, and maybe working there one day, which is in the field of astronomy that we all feel passionate about. So what I'm going to do is just take you through, by way of an introduction, a little bit about the safety track record in space, give you a crash course in drug discovery and drug development, and apologies to anybody who's familiar with that. Spend a while on the effect of microgravity on the human body, and what radiation does, and a little bit about the radiation dose that astronauts may be expected to receive, particularly on a journey to Mars. And then ask the question, well, where can space help in drug discovery and drug development? Touch a little bit on regenerative medicine and human enhancement, very future looking, but maybe closer than we think. The area of synthetic biology is of great interest, and there are already some examples on Earth that may have applications in space, and then summarize. So just by way of an introduction, I thought this is a little bit irreverent, but I've taken this from Monty Python's Life of Brian. What has space ever done for us? And if you've seen the film, the question is, what have the Romans ever done for us? And actually, there's a lot that space has done for us. But before we address that, let's think a little bit about the safety record. So this is quite a busy slide, but actually it's quite interesting because this is the entire list of what has happened in space, not getting into space, where I think we're all familiar, sadly, with the accidents that have happened on takeoff, but actually in space. And at least from what's in the public domain, these are all the safety issues over the last 45, 50 years that have summarized man's activity in space. So very, very few. And the first instance in 1965 was actually when the spacesuit inflated outside of the vehicle, preventing re-entry. And there had to be some manual deflation of the spacesuit, which resulted in effectively the bends. And that, of course, was life-threatening at the time, although the cosmonaut involved, thankfully didn't suffer any ill effects. All of the other effects that you can see since the late 1960s, right the way up to 2016, have been frightening, no doubt. Particularly if you're an astronaut and your helmet starts to fill with water, but have been coped with and have been managed and haven't been life-threatening. So actually that sums up the safety track record while astronauts are in space. And of course, a number of these have been taken from both United States and former Soviet Union missions. So the safety track record is actually very, very good, at least in the short term. And the reason I say short term is that if we have the ambition to go beyond the 6 or 12 months that is normally the residence time on the International Space Station. This is a very short-term type of mission that we might imagine could be lengthened significantly if we were to travel to Mars, reside on Mars, and then either permanently stay on Mars or come back to Earth. So I tried to summarize a little bit drug discovery and drug development in space, and published myself and with the student Phoebe Ryder a review of how the microgravity assist, as we called it, could aid in the assistance of target identification and in drug development. But I'd really like to draw your attention to these two publications by Rebecca Blue, based in the United States. Limitations in predicting radiation-induced pharmaceutical instability. So what's that when it's at home? Well, when astronauts are in space, they're exposed to radiation. I think we're familiar with that, typically galactic cosmic radiation. And that radiation in its own right can not only do damage to instruments and ultimately be harmful to astronauts over a long period of time, but it can induce properties in the active pharmaceutical ingredient of medicines that can make them unstable. So there needs to be quite a lot of understanding of what happens to medicines when they're in space and what the effects of radiation could be. Rebecca also published another really wonderful paper on supplying a pharmacy for NASA exploration challenges and current understanding, and taking some of the work there and marrying it with some of the work that we'd published previously. These two reviews, if you're interested, would give you a very nice overview of some of the challenges that all mission planners will ultimately face for long-term missions. So let's have a little bit of a crash course now on drug discovery and drug development. And you can see, first of all, if you add up the number of years that it takes to get a drug from start all the way to finish, it typically can take between 10 to 12 years. In some instances, it can take a little bit longer. In some instances, it can take a lot shorter. But the reason why it takes so long, I'll explain just now. So if we were to start right at the beginning, this is lab-based work when we're really starting to think, well, what is the latest area of biology that's telling us something about the disease that we want ultimately to treat? And this includes what we call preclinical work. And we would typically identify something that we want to normally block or inhibit, and throw something between 2,000 and 200,000 molecules typically to be able to find something that is a potential drug candidate. And let's say that we found that drug candidate. This is still at the preclinical stage. We submit what is called an investigational new drug application. This has to go through, of course, a lot of rigorous safety review before it gets into the clinical phase. And the clinical phase is phase 1, which is healthy volunteers, which is just to see that the drug is safe and that causes no ill effect. Phase 2 is when it starts to get into patients who have the disease that we want to treat. And this is normally a low number, anywhere between several hundred, very rarely several thousand, but in some instances it can be. And then the phase 3 development stage is normally the large phase studies, which again is the high hundreds or low thousands. And if the drug both works and is safe, then there is what's called a new drug application submitted. This then has a very rigorous regulatory review, and the regulatory agencies all over the world, EMA for Europe, FDA for the United States, CDE for China. Each country has its own regulatory review body that will then, if the drug is safe and if it works effectively, will approve it. And then post the approval, there is what's called a phase 4 study, which is conducted to see long-term effects. So for anybody who takes, for example, and we'll come on to these later in the talk, agents for osteoporosis, bisphosphonates. Those have been in post-marketing studies for many, many years. And this allows accumulation of a vast quantity of safety data, which shows how safe that drug is. Another drug that would come to mind are anybody who has high cholesterol. You're almost certainly going to be taking a drug that's called a statin. Those have been in millions of patients. And we know that they're safe because this post-marketing work allows a very large number of data to be collected. And it's this adverse event reporting, real world intervention studies and observational studies that allow that data to be accumulated. So that gives you a little bit of a crash course in drug discovery and drug development. And what you can see is that we'll start with a lot of molecules here, or candidate molecules, and we'll normally end up with one medicine. And then on top of that, if I was to tell you that the typical drug discovery and drug development process can cost anywhere up to $1.5 billion per drug, you can see that it's not just a long process, but it's an expensive process too. And of course, there are always exceptions to that. But that is by and large the process. So where can space help us? And one of the things that I mentioned around the clinical studies is that clinical studies in healthy volunteers and in patients involve quite a large number of people relative to the number of people that have been in space. I think there's just less than 600 now people that have been in space over the last 50 odd years. So you can see the possibility of being able to do clinical studies either at the early phase or at the late phase just can't happen in space because we can't study enough people at the same time. So where space can help us is most certainly at the early phase of drug discovery in identifying targets for drug discovery and showing that these targets are good targets, and also in what's called indication expansion, which is to take drugs that have been approved on Earth and test them in space, and test them in conditions where we know that they're safe and that they may work. And there is the possibility of doing that, as I'll describe in a moment. Now, when we think about some of the biochemical and biophysical activities, protein crystallization is something that I'll mention in a moment. I'll mention a little bit about structural based drug design, or SBDD. I'll mention a little bit about drug efficacy comparisons, but there are a whole bunch of things here that can be done using that very, very unique environment that there is, for example, on the International Space Station. So you may know studies have been done with plants, studies have been done with microbes. There are a number of animal studies that have been conducted, all under very rigorous scrutiny, of course, but they're invaluable as to what they can tell us. If we look at the far end here, I think we're going to be heading into the age of telemedicine, whether we like it or not, where we will, I'm sure before too long, be able to talk to a doctor, hopefully a real doctor, but the age will come when we talk to a virtual doctor on our laptop, on our computer, on our TV, and be able to tell that person what our condition is, and they will come back to us with a potential diagnosis and even a potential treatment. And that type of telemedicine is already in practice, of course, between the International Space Station and Earth, simply because it has to be. So you can see that there are some ways that both drug discovery and drug development on Earth can benefit space, but also vice versa. So I'm going to sound a little bit like a book merchant now, but I'm not. And if you've never read this book by Scott Kelly, it's a very, very interesting read. It's not too technical if you're worried about it being technical. And it's a very interesting description of his 12 months on the International Space Station. And it's called Endurance, typically because that was an endurance for him. And I won't spoil the story by telling you what's in it, but you can get these now probably in secondhand bookshops and certainly on eBay if you're interested. They're not that expensive. But the reason I illustrate it is that Scott Kelly is one of the Kelly twins, and the NASA-based twin study is a very famous study because it compared Scott with his brother Matthew. Scott spent a year on the space station. Matthew spent a year on Earth, of course. He didn't go into space. And pretty much everything that you could measure from Scott and from Matthew was taken. So they were able to do biochemical analyses, monitor cognition, do what is called genomics, look at the gene expression, immune response, measure metabolites, it's called metabolomics, in blood, in urine, measure the microbiome, and of course the microbiome is what we all have in our lungs and in our gut. These are the microbiota, the bacteria that keep us healthy. And I'm sure everybody knows you are what you eat, and actually it's what you eat that keep those bacteria, keeping your immune response primed and ready to go. And proteomics, which is what your protein content is, physiology, and telomeres. Telomeres are very interesting. They're repeats of nucleic acids at the end of our chromosomes. And as we age, our telomeres shorten. And NASA were very interested to see, well, what would happen to the telomeres in Scott and Matthew Kelly, given that they were in two very dramatically different environments. And this paper is a landmark paper published in Science in 2019. And I believe that is free and open access if you're interested in it. So I'll come on to a little bit about what that data showed in a moment. But before I do that, just like to mention some of the physiological effects of microgravity. And I think the ones that we'll be familiar with are a decrease in muscle strength and a decrease in bone density. And for those of us old enough to remember the Apollo missions of the 1970s, when the astronauts landed, you wouldn't see any of them walk away from the vehicle when they were brought out of the ocean, and that's simply because they couldn't. They'd lost muscle mass, they'd lost bone mass. They were actually trying to re-equilibrate into being into gravity and having an up and a down, because of course in space there is no up and there is no down. And this leads to space motion sickness, leads to neurovestibular dysfunction, which is effectively a disturbance in hand-eye coordination. It leads also to a decrease in cardiovascular efficiency. And again, what's that when it's at home? Well, it's how hard your heart has to beat, effectively. And our hearts beat normally because they're counteracting the effect of 1 times gravity on Earth. But if there is no gravity, your heart doesn't have to work as hard because there is nothing to push against. There's no force to fight. So cardiovascular efficiency decreases, blood plasma decreases. As a consequence of a consequence of a negative calcium balance, there's an increase in renal stone risk. And there's interestingly an increase in fluid redistribution to the upper body and the head from the lower extremities. If you imagine that astronauts, of course, are effectively extremely fit athletes, redistributing 2 to 3 liters of fluid from your lower extremities to your upper extremities might not be a problem for some of us, but certainly for astronauts who are very lean and, of course, very physically fit. That's quite a lot of fluid. And that leads to a condition that I'll show you in a while. So I mentioned the NASA twin studies. There's been some very, very interesting findings. And again, this is the paper that was published in Science, effect of 1 year in space on longer chain fatty acid desaturases and elongases, showing an effect on fatty acid metabolism, showing an effect on some of the measures of biochemical research, facilitating the hazard risk assessment of long-term space flight missions. And again, I think these papers are open access and they're very interesting. Now, one of the things that is the most interesting, I think, is that there does appear to be a decline in the immune response. And of course, that's probably natural because the International Space Station, of course, is a closed environment. Unlike us on Earth, we're not in a closed environment. And so we're constantly being challenged by bacteria and viruses. And of course, with the International Space Station being a closed environment, it's not being challenged. So the immune response does seem to be negatively affected. And that begs the question, if maybe many, many centuries in the future, we were to be able to travel to other worlds, would our immune response be compromised in some way that may make it less effective? So what happens in space? Bone loss. I said I'd mention bone loss. Well, in bone density, it decreases between about 1 to 1.5% of bone tissue lost per month. And even in astronauts that are extremely fit and they've spent 3 to 6 months in space, it can take up to 2 to 3 years to regain that bone mass back on Earth. So there's some interesting data here, and this is summarized over a 3-year period. So if we regard, for example, that we're going to take about 6 to 9 months to get to Mars, we're going to spend some time on Mars, and we're going to spend some time coming back to Earth. What do we predict might happen to the pre-flight bone mass? And the comparison here is actually 2 years postmenopausal women. It's only a relatively small group, but this data is pretty consistent. And this shows here the gradual decline in bone mass. The data that we have so far from 22 astronauts is over 6 months. And you see, we're looking at around 6 to 7%, pretty close to what I said here, 6 to 7% over the 6 months. So what would happen over a 3-year period? And would it continue to decline and maybe gradually plateau off? Or would it just completely decline at the same rate? And if we were to imagine, for example, a 25% reduction in bone tissue over the period of a 30 months mission, that's actually a very, very serious amount of bone loss. It's not just the bone, of course, in the arms and the legs that we think about. It's the bones in the sternum that allows for the chest wall to move when people breathe in and out. Losing 25% of bone mass would actually be very, very serious indeed. So what are the countermeasures? And the countermeasures are quite simple. They sound simple. There are effectively resistive exercise and more exercise. And astronauts typically train between 10 to 3 hours per day. And of course, all this is monitored. So there's no sneaking off and not doing your exercise. It's all monitored. There is, of course, a lot of loading that is put in place to help those astronauts try and retain and develop the muscle strength that they need for when they return back to Earth. Of course, they have good nutrition and they take bisphosphonates. So they take drugs effectively for osteoporosis, of course, although they don't technically have osteoporosis. And just to give you an idea of what a cross-section of an osteoporotic bone looks like, you can see this has what's called a honeycomb structure. It's very much like a crunchy bar, if you've had a crunchy bar. And this is the normal bone, which has much more filled in cavities within the bone. So this bone, of course, would be more brittle and more susceptible to fracture. And this bone is a stronger, healthy bone. And this particular astronaut here, this is Kjell Lindgren, using what's called the Advanced Resistance Exercise Device. I think I bought one of these for Christmas not so long ago. And you can see here that it's effectively allowing him to exert force in this particular case on his legs and on his quads. But there are similar machines for working the upper body too. So I thought I'd illustrate a little bit here what happens with bisphosphonates as supplements to protect bone during long space flight. And there aren't many publications on this, and this is the best one. So this was published in 2013. And this looks a little complicated, and I apologize that it's blurred, but actually that's the quality of the figure, unfortunately. So we're measuring here change from pre-flight again, and we're looking at here the neck, the trochanter, the hip, the pelvis, and the lumbar spine. So this is pre-exercise device in the open diamonds. This is after exercise, so you can see there is a move upwards here for all of these different bones. And this is the effect of bisphosphonates. And bisphosphonates, in addition to exercise, also maintain bone mass for all of the bones studied. So this is a very nice illustration of where a drug that's used for osteoporotic patients on Earth is actually protecting against bone loss in astronauts who don't have osteoporosis. They're healthy individuals, their bones are healthy. It's just their accelerated liability for losing bone. And the combination of resistance and the bisphosphonate attenuated this expected decline. And that's a really positive finding. And that substantiates, I think, to me, very simply in this one study, and there have been others, the use of bisphosphonates to protect against bone loss. So I want to mention a little bit now, some examples that are a little bit more recent. So there is an agent called osteoprotegrin, and osteoprotegrin neutralizes the effect of what's called the rank ligand. And the rank ligand is an agent that influences bone turnover, and it effectively influences the balance of bone production versus bone resorption. And if you block rank ligand with osteoprotegrin, it actually counters the effect of bone loss in mice, this time in space. And this is particularly interesting because the human drug denosumab, which also now is used for patients who either don't respond to bisphosphonates or for which bisphosphonates aren't completely effective, also is a very potent blocker of osteoprotegrin and protects against bone loss. So this is another example of where, in this case, an experimental drug tested in space flight in mice effectively reduces bone loss. So I put together here a table here. There aren't that many, again, of agents that have been shown to affect bone and bone loss, hard tissue loss and soft tissue loss, and muscle is the soft tissue. So I've mentioned osteoprotegrin, and there are some details here of positively affecting bone strength, biomarkers of bone resorption. There's an agent here called myostatin, which inhibits skeletal muscle atrophy. And again, this is an experimental agent that's been tested in animals in space. And there is a human analog of the agent called sclerostin. So this is romosozumab, which also effectively protects against soft tissue loss. There's a very interesting drug here, so formoterol. So if anybody is asthmatic on the call, you will almost certainly be taking a long-acting beta agonist. And formoterol is a drug manufactured at AstraZeneca, salmeterol and salbutamol manufactured at GlaxoSmithKline, but it doesn't really make a great deal of difference. They're both long-acting beta agonists, and they're both very good at opening up the airways and relaxing the tissue. So why have I given you that as an example? Well, I'll show you in this slide. I'm sorry, just to summarize here that targeting myostatin, targeting osteoprotegrin, and also having effects on a number of other osteoclast activating systems here positively affect the negative effects of microgravity on bone loss. Now let me come back to the formoterol study. because this was a very interesting paper published just last year. In this particular case, formoterol is very futuristically given into a very small microfluidics dispensing unit. And this nanofluidics delivery of formoterol has been shown to positively affect tissue loss. So what we're looking at here are the effects of formoterol. So this is a long-acting beta agonist drug on muscle loss in mice flown on the International Space Station compared with their ground controls. And doesn't really matter what the different muscle groups are, but you can see here, and you can see here quad weight. In all of these studies, the amount of muscle mass has increased from ground control when given formoterol, but also in space flight when given formoterol. And this is quite telling. And in this particular case, this is measuring grip strength. This is quite telling because it's not just increasing the weight of muscle, it's actually increasing the functionality of that muscle. And being able to translate the increased weight into increased grip strength, I think is really quite important. And I think this will be quite an interesting study for the future. Now, the reason that this is interesting is that it's not just thinking about muscle loss in astronauts in space. We're thinking here about muscle loss in many patients who have neurological conditions where they lose muscle. And particularly patients who have chronic obstructive pulmonary disease, largely as a consequence of smoking, will lose muscle. And if an agent that opens up the airways, that allows them to breathe better with the airways that they have left, hopefully, but also allows the increase in muscle, then it may benefit those patients too. So it's a very interesting study, and it's even more interesting because it's been done with a nanofluidics system or a microfluidics system, but it's called nanofluidics, where this is a reservoir that's actually injected subcutaneously. So it's possible to have continued release of this drug into this in these animals in this study. So let's go on to a little bit about crystallization now. And I think this is important because NASA has put a lot of effort into understanding how microgravity can affect crystallization. So this is human insulin in the figure here. And these are insulin crystals that you can see on the right-hand side, not particularly high quality, different shapes. These are insulin crystals grown in space, much higher quality, larger, and tend to be better structured. So why does that matter? Well, the reason it matters is, let's just say we want to understand where we can target a drug to our protein. So it can be any protein. And let's just say in this particular case, we want to target an enzyme. If we can make good quality crystals of our enzyme, we can determine the structure of the enzyme using X-ray diffraction. And using X-ray diffraction, we can then, on our computers, not necessarily in a wet lab, but on our computers, do what's called structural-based drug design and be able to target a drug to the binding site of that enzyme. So I've illustrated this just figuratively up in the top right here. Let's say this is our binding pocket. This is an enzyme here. I've just made it up. Let's pretend this is an enzyme here. This is our binding pocket. We've determined this structure from crystals in the bottom right, and we now want to fit a drug into this binding pocket. And we can do that on our computers. We don't necessarily need to go into a lab to do it. And that's really important because it shows the value of microgravity in producing good quality crystals. And I'll try and illustrate this in this little cartoon here. So on Earth, we're trying to make crystals here, and the proteins are coming together. The individual units within the protein are coming together, and they're coming in a way that's quite random. In microgravity, because of course there is no gravity, so the crystallization process is much more gentle, if you like. That's a simplistic way of looking at it, but it effectively means that there is no forced forced sedimentation of the individual protein molecules. So they come together, and that is the simple reason why, by and large, protein crystals can be of higher quality when grown in space. So again, I'll give you some examples here. So reverse transcriptase, when I was working in HIV research, this is in the 1980s, the Wellcome Foundation were leading in the development of AZT, reverse transcriptase inhibitor, that blocks the virus that causes AIDS. And at that time, were really desperate to be able to get crystals of reverse transcriptase. They couldn't get crystals on Earth. And at that time, of course, this was the late 1980s. Of course, it was quite a big thing to be able to put crystals up into the space shuttle. Of course, the International Space Station wasn't there. And lo and behold, space-grown crystals were larger and better ordered. And that for certain helped the Wellcome Foundation be able to develop crystals to reverse transcriptase. There are a whole bunch of other drugs, Keytruda, a key drug for patients with cancer, alpha interferon, some other earlier stage drugs here have all benefited from having crystal work done in space. So growing crystals in space can produce better structures. Better structures can help us with what we call rational design. Rational design can produce new drugs faster. And then these faster leads might accelerate the drug discovery and development process. So again, this the value of, I believe, of microgravity in helping this particular phase of drug discovery is unquestionable. And of course, it makes use of the fact that we don't have these microgravity conditions on Earth. We can simulate them to some extent, but we don't have the luxury of the environment that there is in the International Space Station or the Space Shuttle in the early days. So there's a whole technical program now that is based on the ISS. And again, this particular document is free on the internet if you're interested in it. This is the drug Keytruda, pembrolizumab, microgravity crystallization experiment, published in Nature Microgravity in 2019, and that for certain helped in the discovery and ultimately development of that anti-cancer drug. This is how it's done today, and this is quite interesting. This is the little porthole here in the International Space Station, and this is the crystallization experiment in progress. It's simply allowed to float around here. There is, I think, a net under here that stops it wandering around the ISS, but the simple crystallization experiment is done in these microtiter plates. Amazing. So we're going to mention a little bit about radiation. And the reason I mention this is this leads into the last part. So if you're not familiar with what a millisievert is, don't worry about it. But if living on Earth, we'll be exposed to about 2 of them. If you live or work in a power station, you'll be exposed to about 20 of them. 100 millisieverts there or thereabouts is the level above which cancer is predicted to be more likely. And of course, that's only a guideline, but anybody living and working in a power station is well under the limit. If you're on the International Space Station, you're about 2 times over the limit for exposure to levels of radiation that would make cancer more likely. And of course, that depends on how long you're on the International Space Station. But certainly if you're there for many, many years, which we aren't yet, this would be a concern for astronauts. And should we ever get into interplanetary space, the level of radiation is much higher. That's around 600 millisieverts. And the reason I put that on here is that it's quite germane when we think about transport or travel to Mars, because Mars receives on average, let's call it 100 times the radiation received on Earth. And NASA have estimated a career whole body dose for astronauts to experience radiation during their lifetime. This increases as you get older, And that's not because we're more resistant as we get older. It's effectively because we've got longer to live. Sorry, it's because we've got shorter to live. So the lifetime exposure limit is lower as you are younger. It's actually slightly higher in men than it is in women. And as we get older, because our lifespans are going to be shorter when we're in our 40s and 50s, as opposed to our 20s, the level increases. And the reason that this is important is NASA's own studies have shown that astronauts will exceed the lifetime exposure limit for exposure to radiation on a 3-year mission to Mars. So the radiation that astronauts receive right now is a limiting factor when we think about long-term space missions. There's a very fascinating piece of work that's being done by an international group of astronauts here and scientists working on what they call a radio resistance roadmap. And the reason it's interesting, I'll try and illustrate it in this next slide. So you may have come across these particular beasties called extremophiles. So Deinococcus radiodurans is an extraordinarily a bacteria that can tolerate extremely high doses of radiation. So again, if you're not familiar with a gray, and it's denoted GY here, don't worry about it, but 5 to 10 of them would kill us. These bacteria can tolerate 15,000 gray, and they can't just tolerate it, they appear to thrive in it. And this little beastie at the bottom, which I think everybody's probably seen, an example of the tardigrades, they can tolerate just about anything. It can tolerate very high temperatures, very low temperatures, very high pressures, but also very high doses of radiation. So what scientists have done is they've thought, well, what is it about these beasties that make them so tolerant of radiation? And can we isolate it? And can we understand, could it have potential benefit for animals and for human beings? So what they've done is they've isolated the protein responsible for protecting from the effects of radiation, which they've called Desup. And they've combined this Desup and they've cloned it into human cells that have then been irradiated with a dose of radiation. And they've looked at the viability of cells throughout the course of the study. And what they found is lo and behold, the viability starts to drop off as the dose and the time increases. But the viability actually is maintained and actually starts to increase when this Desup protein has been cloned into these cells. So this begs the question, this is, of course, is only done in cells grown in a laboratory, but it begs the question, could this protein have some positive effects on radiation sensitivity in human beings? And it's not an impossibility, it's an impossible today, but it's not an impossibility to think for the future. Is this a way of maybe expressing this protein in human beings to make them become more radio resistant? Now, I should say that the mechanism by which this happens it doesn't just put a fantastic little shield around the cells and protects them. What this Desup protein appears to do is repair radiation damage extremely efficiently. So cells are still affected by radiation, but the damage that the radiation causes is repaired very effectively by these proteins. So it's something to think about for the future, because I think we'll see this exploited in several different ways. The other way that it may be exploited, of course, is that sadly, patients who have cancer, when they're given radiation treatment, the tumors sometimes don't respond to radiation therapy. And understanding the mechanism behind that is really useful to be able to target and disrupt whatever pathways there are that are protecting those cells from being killed, because that's what we want to happen. So there are ways here that I think we can benefit both medical discoveries on Earth and possibly at some time in the future benefit human beings in space. So I want to mention a little bit about 3D bioprinting. So 3D bioprinting, this is a company based in Russia. They've conducted what they call magnetic levitational bioassembly. And let me just go to the slides here, because what they've shown is that they can start to put together in the same way that we would use in a 3D printer, where we use bioink to maybe build a structure. They can start to build now primitive tissues using different cells as the bioink. And they can start to build up, in this particular case, it's a very primitive cartilage type molecule and a very primitive thyroid gland type molecule. They're actually called thymocytes. It's not an intact thyroid gland, and this isn't an intact cartilage. It's a chondrocyte. But they're starting to build up, perhaps, the framework for what might be organ synthesis in space in future. And why does this excite me? The reason it excites me, again, is that this would be very, very hard indeed to do on Earth, because the microgravity environment here provides no constraints. There are no boundaries around being able to grow tissues, possibly being able to grow organs in future in space. And that's what microgravity can bring for us. So I want to finish with something that's a little bit now futuristic, which is human enhancement in synthetic biology. And maybe a couple of questions as to ask it, well, is it realistic? Is it advisable? Is it ethical? And actually, is it essential? So when we think about human enhancement, we might think about Arnold Schwarzenegger walking around the planet. But actually, the human enhancements that we're familiar with have been with us a very, very long time. And I was surprised when I first researched this, that back well before the Christian era, that the concept of a glass as a magnifier has been well documented by this particular chap. Seneca used a glass globe of water as a magnifier. And of course, what we would call enhancements to vision or spectacles have been around for many, many hundreds of years, really since the 1300s, and of course all the way through since. So there are many agents or targets that have been used that are by way of an enhancement, whether or not they be prostheses for people who have had limb replacements, but they can of course include performance enhancing drugs and any of the agents that may be replaced due to either life-threatening or non-life-threatening elective surgery. So human enhancements have been around for a long time, but what we're getting to now is maybe something slightly different. So this is quite a complicated slide, and I'll just go through it very quickly. So endogenous gene therapy. So if you've come across this before, this is effectively for somebody who's deficient in a gene, can be given gene therapy, and will allow that gene to be expressed in their tissues. There are a number of approved products now for gene therapy. The area that is a little bit more controversial is actually being able to edit genes themselves. So if one has a gene that's defective, the technology exists, at least in theory, to be able to edit that gene in human beings. It's certainly been done in animal models. There are clinical trials in human beings, but there is the possibility to be able to edit that gene in future. What is very controversial is what's called germline gene editing, where you would edit not just your genetic makeup in the individual, but you would edit the genetic makeup in a way that it would be passed on to their offspring. And this, of course, is effectively irreversible. And there was a very infamous study conducted in China a few years back, for which we believe to be the only known example. So why am I mentioning this? And the reason I'm mentioning this is if you think back now to the example that I gave about being able to confer radio resistance, would it be possible at some time in the future to be able to gene edit the makeup of astronauts to make them less susceptible to the effects of radiation, make them less susceptible to bone loss and muscle loss? And there are, let me just go to this slide, there are a number of potential targets now that have been implicated in all of these things, in radiation protection, prevention of hard tissue loss, reduced demand for oxygen, which is very interesting. So these genes here have been isolated from individuals that live in the high Tibetan plateau and in high parts of the world that we would probably, at least I would, struggle to be able to breathe properly. These people can do this quite easily. And I put this one in just as an example. So this is a genetic modification, a natural genetic modification that's found in South Korean people, where they still sweat normally, but they don't produce body odor. And of course, this is quite interesting, at least from the cosmeceuticals industry, because they're quite interested in, is this a potential group of people that may or may not benefit from non-scented antiperspirants? Why I think this is quite interesting, and it's a little bit tongue-in-cheek, but if you imagine perhaps that we're going to have colonists in confinement for the future, it might be possible, for example, to select people who are not only less susceptible to radiation damage and tissue loss, but actually don't produce body odor. And that sounds trivial and trite for us sitting here on Earth, but when you come to look at some of the psychological evaluation of astronauts in close confinement, there are some very small things like this that can really disrupt the success and harmony of the mission. So, finish up with the last couple of slides here. And synthetic biology, particularly as applied to crop enhancement, is something that has been around for some time. Excuse me. Biofortified crops are being produced that express different levels of vitamins, minerals, metals, amino acids. We have drought-resistant plants. We have plants that can tolerate temperature extremes. We have plants that can tolerate dust, that have a faster growing cycle, higher yield, higher photosynthesis, and enhanced nutrient uptake. So all of these types of modifications may have implications for not just growing crops, perhaps, on the International Space Station, but perhaps if we ever get to the point of colonizing the Moon or Mars, probably Mars, where there is perhaps the possibility of being able to live, albeit in gravitational conditions that are more amenable to human beings than on the Moon, but still restricted, may give us the opportunity to provide some form of sustainable supply chain for food. So I think we'll see quite a lot of interest in this area in future, particularly when it comes to the application of synthetic biology to astronaut maintenance of food supply chain. So last couple of slides. So what may the future hold? I hope I've shown you that protein crystallization has been of interest, target identification, the idea of being able to block agents that disrupt bone and muscle atrophy. Haven't mentioned anything about drug stability apart from the radiation effect that I told you about right at the start. We have mentioned something on 3D bioprinting and tissue regeneration, touched a little bit on clinical testing. And then, of course, there are now a very expanded set of machine-based learning algorithms that may help us with telemedicine in the future. Last but not least, what could the future hold? Just by way of a summary, I think the space environment does give us really ample opportunity to find new drug targets and to be able to test appropriate medicines. Does give us the opportunity for development of tissue engineering biosystems. Does also, I think, start to seed in our minds, is there the potential for human enhancement driven by a terrestrial need? And I see a real partnership here between these applications and development in space and what patients and what we as human beings want on Earth. And I think there's a very beneficial symbiosis between this type of work in space and the requirements on Earth. And lastly, of course, development and deployment of synthetic biology applications. One of the best known examples is golden rice, as it's called. So this is a genetically engineered rice that's been made to express higher levels of vitamin A. And that's simply because for many people who have rice as their staple diet, they're lacking the ability to have vitamin A. So the development of golden rice, as it's been called and now approved, is specifically to meet that need. So what has space ever done for us? I hope I've shown you, at least in this just over, where are we? Just under an hour. At least I've shown you, I hope, that space has done quite a lot for us, and I'm sure it will continue to do so over the next 5, 10, 15 years. Let's keep the International Space Station afloat, because that's giving us a fantastic laboratory to work with. But whatever replaces it in future, I think we owe a big sense of gratitude to everybody who's supported that. So last but not least, thank you very much for listening, and I'll do my very best to answer any questions if you have them.
Thank you, Martin. That was an excellent talk. I must say, I've learned a lot about space medicine. There's loads of things I didn't know. Might even help me with my application to become an astronaut. But we asked people to put questions in the chat box. Anne and Mick Dunn have asked, great talk, fascinating. Have you heard of CRISPR, and has it been tried in space?
It hasn't been tried in space. There is a clinical study at the moment where it's being tested in patients that have a very rare eye disease that will lead to those patients becoming blind. And I think the whole world is waiting to see how effective this will be, because if it is effective, it will open up the doors for a lot of other rare diseases on Earth. And eventually, I think once we as society are comfortable with the ethics behind it, I think it will be tested in space, but not yet.
I might throw in a question of my own then, if anyone else, by the way, if anyone wants to pipe in with the question, I think it's okay if you turn off your audio and actually ask them verbally. But I was just a little bit confused about the loss of bone mass, the 5% or so on a 6-month stay on the International Space Station. Is that using the exercise and the drugs, or are the drugs not approved? Or
no, that's actually still using the exercise and the pharmaceutical intervention. So you can imagine what would happen if they weren't being used. I think the bone loss would be even more dramatic.
And is there any data from, was it Valery Polyakov, I think, had a 14-month stay in space?
Yep.
Did he measure, I mean, would he be an extra data point? Because I showed you projecting that chart off for a 2-year mission, and does it tail off, or does it go linearly straight down? Was his long duration stay any use?
I tried to find that, and it's not published anywhere. I'm sure the Russian space program must know, but it's not published anywhere. But you're right, and he holds the record, I think, doesn't he, for the longest period in space? So it'd be very interesting to know what shape he was in when he came back.
Yeah, and I think he was a medical doctor as well.
Yes.
What about Scott Kelly with his 12-month stay?
Yeah, so the Kelly twins, when they measured their bone mass, I think they lost about 8%. So it didn't look to be at least going along that linear curve, and it may be because it's starting to plateau out, or of course it may be individual variation. It's a little hard to tell, but they did lose certainly consistently more muscle mass over time, but they didn't lose 12% over the 12-month period.
Right. Well, so if anybody else has any questions, don't be shy. I'll steal the. Oh, here's a question. I'll defer to Tom Finnegan, who said, will we ever get past the ethics of genetic engineering to be able to enhance certain humans, say astronauts, or does it become a free-for-all license?
That's a really good question, and I think it probably becomes a free-for-all license. I think it's, oops, excuse me. I think it's a very difficult question to answer from a pure ethics procedure point, because I think you can imagine perhaps the only way that we would make these type of enhancement procedures widely available is if there is almost no alternative. And heaven forbid if we ever get to the point where we have to almost evacuate Earth to colonize another planet. I wonder whether, if there is nothing whatsoever to lose, then that's the situation where this type of human enhancement would happen. But I've been thinking about this a lot and talking with a lot of colleagues. And if you were to think about this from an ethical point of view, from a drug regulatory point of view, what reason would you take a healthy person and say to them that we want to genetically modify your genes because we're going to make you less susceptible to the effects of radiation that we're going to put you in when you're in space? It opens up all sorts of ethical challenges that I think are very difficult for us to grapple with. But then at the same time, if we seriously want to travel within the solar system, at least in our lifetime, hopefully, maybe beyond, for younger people that might be on the call, we have to overcome the effects of radiation. There's no doubt about it. And nothing is going to stop that from happening unless we decide that we're just not going to have longer term missions in space. So I think that's the problem.
Brought with difficulty. Another question here from Jim Kiron, who asks, and I'll try and pronounce these drug names correctly. Great talk. You said that Osteoprotegrin prevented bone loss in mice in space. Is it suitable for human trials?
Yes. So the human analog, excuse me, is the drug called denosumab, which is now approved for human use. So yes.
Okay, Kathy has another question. What happens to telomeres in space? Was there a difference in the Kelly twins when tested?
Yeah, well, it's very interesting because they became shorter in space. So it actually might argue that space in its own right is affecting the aging process and negatively affecting the aging process. Now, when Scott came back, there were a whole bunch of things that were remeasured, and there did seem to be some readjustment back to normal. But if I remember rightly, the telomere length was still shorter in him when compared with his brother, with his twin.
Okay. Bernadette Pierce asked a question. This might refer to something you were saying. If you want to turn your audio on, Bernadette, and ask directly, the question is, what effect has this on bone marrow?
On bone marrow itself, I don't think there is any effect on bone marrow, not that I'm aware of. I think the bone vascularity is negatively affected. And it's probably not impossible to see that if the bone structure starts to go on the route towards disintegration, that there will be some leakage within the bone itself. But I'm not aware of any effect on the bone marrow.
Okay. And Edward Malarkey asks, thanks, Martin, very informative. Pharma is a very complex area. Do you know of any online free pharma foundation courses?
I don't, but I'm a big fan of the Coursera MOOC platform. And that's just spelled course and then RA. And if you look on that, I'm sure you'll find some, and they're all free. So Coursera is definitely one I would look at. I've done all the astronomy ones on there. They're all free, and they're fantastic.
Right, well, I think that's the last formal question. I might abuse my position and ask one extra one. That drug Desup,
Yeah. Yep.
was that space inspired, or did it come from a terrestrial trial or need?
What's really interesting is I'm sure the radiation dose that Deinococcus radiodurans can survive exceeds the natural radiation dose found on Earth. So it sort of begs the question, why would an organism be able to tolerate a radiation dose that it isn't never been naturally exposed to, at least on Earth? So that makes you wonder, has it come from somewhere where the radiation dose was higher? And in a way, it sort of fuels a little bit of the panspermia hypothesis that maybe some of the microbes that are on Earth have been in environments where the conditions have been so extreme, they've naturally been able to develop this type of defense. So it may well be that these organisms have either experienced radiation on Earth that we didn't know about in Earth's history, or that they've experienced an off-Earth radiation dose that can only have come from them having come in comets or meteorites.
Okay, well, we might leave the formal questions there, but I just need another 5 minutes to tell you about the eclipse that is coming up and the next talk, if you want to bear with us for 5 minutes more. And if anybody has a question in the meantime, when I stop talking, I'll just quickly have a look, and or at the end, just pipe in with your audio. If you have anything from Martin, because it's not often we have an expert like this. It really opened my mind up to the whole space medicines. And it's a thing we've referred to, what uses space, and to actually see the hard and fast figures from a researcher involved in this was very informative, I must say. I enjoyed this talk enormously. So thank you for that, Martin. Do stand by. Everybody else stand by as well. I'll just go through my notes here of what's coming up in the future. Here we are. So a lot of what we're going to talk about is in the magazine, so I'll be very brief. There are diagrams in the magazine as well, the visuals there. A quick review of what's happening. There's that nova in Cassiopeia. Mars is going to pass very close to the moon. Bit of a meteor shower, but the moon interferes. Mercury, before the next lecture, is going to be a superb sight in evening skies, and it'll pass the Pleiades star cluster. Even Jupiter and Saturn get in morning skies. You like getting up the crack of dawn. When you can also see that morning comet, remember, Comet Atlas. And I'm going to mention at the end the eclipse that's coming up on June the 10th, because it's quite well placed from Ireland. So quickly, just to rush through those, one of the big things is Mars on the 17th of April. I have some other notes, just gives me the days of the week. Let me get that up. There we are. Yeah, this Saturday, Mars will be very close to the moon, about 1 moon width away from the moon. Now, the only problem is that happens in daylight. But I have seen Mars in daylight with a pair of binoculars. You'll certainly see the moon with the naked eye. So I think anyone who's got binoculars should point them at the moon on Saturday. There's full details of this in the magazine, including a diagram of where it is above the moon. The moon will be about a quarter of its diameter will be lit up. So a nice fat crescent. So definitely visible in broad daylight if it's clear. And you may see Mars. Now, when I saw Mars, it was closer to the Earth. It was quite bright. Mars is now quite far away from the Earth and getting a bit dim, so it could be a challenge. So we want you to at least go out and try and tell us what you see. And if you don't do that during daylight, then wait till the sun sets around 9 o'clock. You'll see Mars easily with the naked eye. I saw it last night, but we have to see it all this week on any clear night. It'll be about 3 degrees away from the moon at that point in the twilight. That's 6 moon diameters away. So not as spectacular as being 1 moon diameter away in daylight. Them's the strokes, folks. So enjoy that on Saturday and check out the diagrams in the magazine. Even later this week on Thursday, the moon is between the Hyades and Pleiades star clusters, and it'll be a nice thin crescent, 13% of its diameter lit up. That'll be a beautiful sight. The glow from the moon won't overpower the stars. In fact, the brightest star in the Hyades, Aldebaran, will be closest to Mars that night as well. Closest to the moon that night as well, with Mars sitting above them. And in fact, Mars and Aldebaran are around about the same brightness, and they're both slightly orangey in color. So it's almost like having a very widely separated double planet these last few weeks. You'll also, the day before that, Wednesday night, see the crescent moon below the Pleiades. And again, there's diagrams of this in the magazine. So, Wednesday and Thursday, definitely check out the sky. And again, on Saturday, let's hope for clear skies. Next week, Tuesday, the Beehive star cluster is near the moon. Details in the magazine. I mentioned that meteor shower, the Lyrids, not a particularly strong one, maybe 20 an hour. And unfortunately, there's a bright moon around this year. So it's set for Thursday, the 22nd of April. That's Thursday week. So you can check it. You'll see a few more shooting stars than normal, but we really want a dark rural sky to get the best of a meteor shower like that. Then when we get toward the end of the month, Venus and Mercury come into the evening sky. Venus is going to be very low down, but it's extremely bright, by far the brightest thing in the sky. And it'll be near Mercury. So there's some details of that in the magazine as well. And the May issue that we're just producing this week, that will have more details of Mercury being in the evening sky in early May. Got about 2 weeks actually to see Mercury, so it's quite a good pass. Another thing we told people to watch out for in the magazines at the end of the month, on Monday the 26th of April, Mars passes about a moon diameter away from the star cluster Messier 35 that you can see in binoculars. I think some keen-sighted people from rural locations claim they can see it with the naked eye. So that'll be a spectacular sight in binoculars. And those of you that like taking pictures, that's definitely a date to remember, Monday the 26th of April. Again, see the diagram in the magazine, because actually it'll be fairly close for several days before and after, as the diagram shows. And then the day after that, Tuesday the 27th, is a full moon. It's the pink moon this month, it's called. And it's the second of 4 supermoons in 2021. So you might hear a bit more of that in the popular media. And there's a few bright stars that the moon passes nearby. All those details are in the magazine. So looking further ahead, after our May lecture and our June lecture, on the 10th of June, we have a decent partial eclipse of the sun. I meant to check actually when we had the last one, but I think it was 2015 when we had the last good partial eclipse of the sun. We did run an event for it. So it's been quite a few years since we've had a good partial eclipse of the sun. And in the next magazine, we'll do some research to find out exactly when the next one is happening after that. Basic idea is they're rare. Of course, you have to be extremely careful when viewing eclipses of the sun. If you look at the sun with the naked eye, you can damage your eyesight. Use binoculars or telescopes, and you can seriously damage your eyesight before you can react. So don't do it. Use the guidelines. We'll be putting some on our website, and they'll be in the magazine as well. The simplest way is to cap one side of a pair of binoculars and then project the sun onto a white card through the other side. Don't let any kids anywhere near the setup, because they love to rush up and try to look in. So as long as it's well supervised, you'll be able to get great views that way. We also have some of those eclipse glasses still, and you can either observe the eclipse with them, or you can actually hold them up in front of your smartphone and your camera and record the eclipse that way, because we want to publish all the Irish photographs that are taken at this particularly rare event. So there's loads coming up in the next 4 weeks, and indeed further afield. That eclipse is going to be really something to look forward to. The other things to see in the International Space Station will be in the morning sky. If you don't like getting up early, wait till the middle of May. You'll get to see it in the evening sky. Brightest thing when it flies over. And of course, it's currently actually they sent up more astronauts. There's 7 astronauts on last time I checked, but we can't see it at the moment. When it flies over, conditions aren't suitable for us to be able to view it, unfortunately. But that's going to change. So all this in the magazine. I said you can get the magazine online for £5 or £6, £5.95 I think it is, including the postage, if you want to see what it's like, or just sign up. It costs around €1 a week to be a member of Astronomy. I'll get the magazine, the post every month, and I'll tell you what to see in Irish skies in particular. So that's the Sky Guide. I don't know if anyone's asked any questions. I don't see any there, so I'll just tell you about a couple of quick events coming up between now and the next lecture, and I'll tell you what the next lecture is then. The Sky at Night on BBC4 is on this Thursday night, repeated at 11:55 p.m. in the listing guide I used, so I might want to set your recorder for that. There's 2 radio interviews that I'm doing coming up. One is on this Friday, 12 noon, on Near FM, NEAR, Northeast Access Radio, FM.ie. You can listen online if you don't have a radio that'll pick it up. And then we did a long interview with Phoenix FM actually a couple of weeks ago, but it's not being broadcast until the following Monday, the 19th of April. And that's on between 11 a.m. and noon on Phoenix FM. So if you just search Phoenix FM, I think it might be phoenixfm.ie, you can listen in live to that one as well. And we'll try and put recordings of those on our website. If you go to astronomy.ie/audio, you'll see, I think we have the News Talk interview up, maybe the BBC one we did last week as well. Don't forget the evening classes are enrolling now, even though they don't start till October. They take place online, so anyone around the world can do those. And that'll keep us busy until the next lecture, which I'll now tell you about. Our May lecture on May the 10th, they're usually the second Monday of the month, is going to be given by Paul Evans of the Irish Astronomical Association. Paul gave a first talk about Apollo 11, which was the actual landing on the occasion of the anniversary of the moon landings. So that was 2019. But he's a big fan of the Apollo missions, having grown up with them, and he's going to take the story of what happened after Apollo 11 came back. There were 5 other missions that went to the moon, and there were actually a few others that were scheduled that didn't take place. At least one of them was converted into a space station, and Paul's an expert on all this. So if you like keeping in with tonight's theme of space exploration, then do come along on the 10th of May online here. You can book your tickets on astronomy.ie now. Just go to the events option in the menu on the left, and you'll see each year. Just click this year, you'll see Paul's talk there on the 10th of May. His last talk was absolutely superb, so I'd highly recommend that to you. Don't forget to follow us on Facebook and Twitter for those space station predictions and anything new that happens that we can't tell you about in the magazine or through our members' email. For instance, Northern Lights, we had a few scares about those between this meeting and the last one. Unfortunately, they're cloudy in Ireland, or it happened when it was dark over the USA and not Europe. So we haven't actually had any reports of aurora yet, but we seem to be getting about one a week almost. These tell people to watch the northern sky. So that's everything I have. I don't see any more questions. So with that, I'll thank you all for coming along. But a huge vote of thanks to Martin Braddock for an absolutely thoroughly enjoyable talk. I learned so much. I think I might try and follow you, Martin, see you doing any other talks.
Oh, thank you, Dave. I mean, one of the areas that's I think really quite thought-provoking, and if you've read Martin Rees's book on it is with the artificial intelligence leaning towards it, and there's a few other authors, it actually makes you wonder, as technology develops, a lot of space exploration could be solved without human beings. And it's not impossible, I think, that we'll find at some time in the future that we'll have parallel human missions take place, but also perhaps, you'll laugh at my suggestion, but some form of human avatar type missions take place. And I don't mean the Avatar as in the Steven Spielberg Avatar, but it's getting close, I think, to the point where we'll start to see some form of primitive type of artificial intelligence, I think, be suitable for long-term space missions, where spaceships don't need to be big. They can be very small, and because they're very small, they can be accelerated to very high speeds. That's certainly in the NASA's thinking, European Space Agency's thinking. It's certainly in the tech giants thinking. Elon Musk, the Google teams are thinking this way too. And it's not impossible. And actually, I have a number of books that that I could recommend you read if you're interested in this. So Martin Rees's book on artificial intelligence, he's the Astronomer Royal, of course. Michio Kaku, who's a futurist. But I think one of the most thought-provoking books I've read is by Max Tegmark, and it's called Life 3, Being Human in the Age of Artificial Intelligence. And when you read the first couple of chapters, you'll realize what he's suggesting. And to some extent, of course, that's already here now. A lot of what we see is formulaic, and it's formulaic because there are algorithms that will learn what we like, what we don't like, what we like to buy, what we don't like to buy. So if you can imagine extending that to space travel, I think it's closer than you think.
Very good. And the three people you mentioned there, Michio Kaku, I know I've met him. He's spoken in Dublin before.
Oh, okay.
And Martin Rees.
Yeah.
But I haven't. I've seen it's Max Tegmark, isn't it? I've seen him interviewed on some of the documentary channels.
Yes.
So if there's a book out, maybe he might want to give a talk. I see Tom Finnegan is looking in. If he makes note of that name, we can always invite him. I'll plug his book a bit.
He would be brilliant.
Highly recommended.
I think he'd be brilliant.
Yeah. Okay, well, thank you very much, everybody. I think we'll close the meeting there until 10 to 9. Oh, Tom wants to say something?
No, it's Anne here. I just want to say thank you to Martin. That was so interesting.
Oh, thank you very much, Anne, and nice to speak to you.
Finally. Thanks a million. It was lovely now. Thank you so much.
Oh, you're very welcome.
And Martin, I second that. That was a brilliant talk. Really amazing stuff. Really enjoyed it.
Oh, thank you so much.
Well, you know what, that reminds me, I might just throw in one last question there. Years ago, I remember when interferon was first mentioned, and the idea was it might be a cure for all cancers. It would end up, I believe, just helping with a few.
Yeah.
Was that, I remember them saying something like, to get a sufficient quantity for trials would cost 100 million to build a plant on Earth to make it, but in space it would cost about 5 million. What was the final story of interferon? Does that sound about right?
I think the production issues became much simpler on Earth, so it's now produced on Earth. But simply at those days, of course, this is producing what we call biologics drugs today, and there are many, many of them. But back in the 1980s, early 1980s, late 1970s, there were very few. And of course, that's helped. For example, things like the COVID vaccines that there are around now. And all of the anti-cancer drugs, the latest anti-cancer drugs are immunotherapeutics, which are biologicals drugs that 30, 40 years ago, even if we'd had them, there weren't the facilities on Earth that there are now. So I think we've sorted out the supply chain on Earth that's helped a lot for interferon.
A terrible question to ask. I mean, how long do you think it'll be before we cure all cancer?
I'm not sure about curing all cancer, but I think the days are coming where life expectancy will be increased a lot. There are still some cancers that are very difficult to treat. So ovarian cancer is one, and that's simply because it's not diagnosed until it's so late. That's why it's called the silent killer, because by the time it's diagnosed and women recognize it's a problem, it's actually gone beyond the point where it can be treated. But I think the age now of health screening, providing, of course, people comply with it, is far advanced from what it was even 10 years ago. And being able to pick up molecules in the blood or in urine or even in breath to some extent, that can show that there is a presence of something not quite right, I think is really, really helpful. And there's an interesting little add-on to that. So if you've ever heard of fraction exhaled nitric oxide, so this is what we would exhale. And of course, we measure this a lot in clinical trials in patients with asthma, but it's a very good marker of lung inflammation. And fraction exhaled nitric oxide, or FeNO as it's called, is measured on the International Space Station, simply to see, do astronauts have breathing difficulties because of the dust that there is on the ISS. And the dust comes from all sorts of weird and wonderful areas, mostly from human beings because it's actually skin cells. But whatever astronauts take on board the ISS isn't completely decontaminated. So there is some dust on it. And scientists at University in Stockholm have measured a way to monitor astronauts' lung health by measuring FeNO. So that's just one example, and there are many of them that I think are now more routine today. But of course, people have to be willing to have things measured, and I think that's always going to be the difficulty. If you're worried about your doctor finding something and you don't have it measured, then you can't really turn around and say, well, I wasn't treated in time. We have to put ourselves up for this, I think. It's like having your annual health check.
Definitely will be prioritizing that. Tom, do you want to add anything, or shall I close the meeting? Because I see your video on there.
Hi,
You're
Tom.
muted at the moment.
Great talk, Martin. No, I've nothing to add, Dave. I just had the video on there, yeah.
Okay, well, thank you once again, Martin.
Thanks a million,
and
Martin. That was brilliant.
Thank you very much.
hopefully our paths will cross again soon.
Yep, hope so.
Good luck to everybody in Sutton and Mansfield.
Thank you.
Martin has
Bye now.
another article coming up in the magazine.
Yep,
Oh, great.
yep.
Which issue is that, Anne? Is the next issue the May issue?
Hopefully, yeah, we're fairly full, but I think we're going to try and get it in. Yeah.
Terrific. I look forward to that. Oh, there she is.
Hi, Anne.
Okay, everyone, have a safe
Bye,
evening. We'll see you
Thank
all next
you.
month. All the best
Okay.
now.
Bye.
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 Okay, good night. Take care. Night, night.
Leave.
Right. Leave. Oh, okay.
You finished anyway, so.